Hello everyone, welcome to the April 1st edition of Math 262. Reminder that you have WebAssign due on Friday. So today we're going to investigate those power series from last time a bit more, and we're going to see how you express functions you know in terms of the power series. So let's look at an example of a function that you know pretty well, 1 over 1 minus x, and let's call this f of x. So where have we seen an expansion of this before? Does a over 1 minus r ring a bell? Well, if so, that's because it's an infinite geometric series, and this should be equal to 1 plus x squared plus x cubed plus x to the fourth, and so on. We know that adding up this infinite geometric series is the same as that fraction right there, the 1 over 1 minus x. And where does this series converge? We all know that this series converges if the absolute value of x is less than 1. All right. Well, let's take a look at Desmos and see what that looks like there. So on Desmos, if we look at this curve right here, the bolded black curve is the curve 1 over 1 minus x. And then I have two vertical lines at x equals -1 and x equals 1. And then I have part of the approximation of that series in blue. And you see that it works, it does a pretty good job of mirroring the curve in the range from -1 to 1. And I can add more terms to my curve if I want to become more precise. And I see that as I add more terms, it becomes more and more precise in the interval from -1 to 1. And outside that interval, it's not close at all. So what's going on here? Well, let's go back to our whiteboard. What's happening is the following phenomenon. We have a function, f of x, and that's equal to 1 over x minus 1. And the graph of this function looks something like this. There's a vertical asymptote, and it's 1 minus x, 1 minus x. And the curve goes up like this and over like this. So the domain here is all real numbers except for 1. But when we look at our series, our infinite series over here, the sum from n equals 0 to infinity of x to the n, which is 1 plus x squared, ... That only makes sense in the range from -1 to 1. So that series right there, you still have this vertical asymptote, but the series only goes like this. That's -1, and that's 1. So we see that our infinite series has a much smaller domain than our function did to begin with. So what we're going to see as a general phenomenon is that our power series only work in a certain range of values for our original function, 1 over 1 minus x. So we cannot express all of 1 over 1 minus x by a single power series, but you can express part of it that way. So what do we do if we want to write 1 over 1 minus x as a power series centered at a number c. Remember, a power series centered at c looks something like this. So the first power series we had was centered at 0, and maybe we want to center it around a different number. Well, the key is to remember what the formula for a geometric series is. The formula for a geometric series is a over 1 minus r and this is a plus ar plus ar squared plus etc. So what we're going to do is we're going to manipulate our expression 1 minus 1 over x to get it in a form like a over 1 minus r and r is going to somehow involve the term. It's going to involve the expression x minus c in some way. So let's do an example. I think you'll see how that works. Let's set c equals 2. So we need to modify this expression in the bottom till the r piece of it becomes something involving x minus 2. So here's what we can do. We can say that we are subtracting x minus 2, and therefore this piece right here must be -1. You can do a quick check in the denominator to see that I have not changed the denominator at all. I've just rewritten it. So we can multiply the numerator and the denominator by -1, and we get 1 over 1 plus x minus, sorry, -1 over 1 plus x minus 2. Well, that's fine, but we need this needs to be a minus sign, just like up here. They don't match yet. So the way we remedy that is we write it as -1 over 1 minus a minus x minus 2. All right, so this is my a and this is my r. So this should equal the sum from n equals 0 to infinity of a times r to the n, which is the sum from 0 to infinity of -1 times minus x minus 2 to the n. In other words, that's n equals 0 to infinity of -1 times -1 to the n times x minus 2 to the n. And if we just manipulate that a little bit more, it becomes -1 to the n plus 1 times x minus 2 to the n. And this is our power series about centered at x equals, or at c equals 2. This is our power series for 1 over 1 minus x centered at c equals 2. So let's actually see that this makes sense. It should converge on the interval from 1 to 3. So let's take a look at Desmos and see if that matches what the math says it should. So we're using the same function, 1 over 1 minus x, but we're going to use a different approximation. So let's slide this over. And our function is going to, we're going to expand the series from before. So it should look something like this. It starts with -1 plus x minus 2 minus x minus 2 squared plus x minus 2 cubed minus x minus 2 to the 4th plus x minus 2 to the 5th minus x minus 2 to the 6th plus x minus 2 to the 7th. And what I notice is that my approximation is getting closer and closer to my function, 1 over 1 minus x, between 1 and 3, just like our series predicted. I see here with my 11th degree, I'm getting very close. All right. So you see that as I increase this degree, that's like adding up the terms of the series, it's getting closer and closer and closer. Okay. So I'm going to do one more example where we find the power series, and then I'm going to give you 2 examples to do. Okay. So I want to find the power series for the function 1 over 6 minus x centered at c equals 1. So remember, I'm trying to reduce it to the form a over 1 minus r. So I take my fraction 1 over 6 minus x, and I need to be subtracting something like x minus 1, and I see that to do that, this needs to become a 5. So I can check that if that's 5, nothing has changed. All right. So now what happens is, right now, this is a 5, but it really needs to be a 1. So how can I get that? Well, I can multiply the numerator and denominator by 1/5. And then this becomes 1/5 over 1 minus x minus 1 over 5. And so I see here a is 1/5 and r is x minus 1 over 5. And so then this series becomes the sum from n equals 0 to infinity of 1/5 times x minus 1 over 5 to the n, which if I simplify a little further, becomes x minus 1 to the n over 5 to the n plus 1. All right. And we can check that this series has radius of convergence 5, and it should converge on the interval from 6 to, I think, -4. Should I actually work this out? All right, so I'm going to give you 2 examples to write the power series for them. And so do these in your notes. So I want you to find the power series for 1 over 1 minus 3x about c equals 0. That one's not so bad. And then another example, which might actually require some work, is to find the power series for 5 over 2x minus 3 about c equals -3. All right, so do those in your notes. Now we're going to transition on to what are some operations we can do with power series. That is, if I have some power series, what can I do? So there's a lot of things you can do, but I'm going to describe what they are right here. So we're going to assume that f has the following form, and g has this form. Okay. And it works equally well with power series centered at numbers that aren't 0. The first thing that happens is if I want to multiply x by a constant on the inside of my function, that's the same as multiplying it by x inside my power series. If I want to raise x to the n inside my power series, you want to do f of x squared or something, you just do it in your series as well. Remember, when you take an exponent to an exponent, you multiply in the exponents. And last but not least, if I want to add or subtract two power series, that's like adding or subtracting the terms of those series. All right. So let's do a little example with that property we just learned. So we know that 1 over 1 minus x is equal to this sum on the interval from -1 to 1. Furthermore, we know that 1 over 1 plus x is 1 over 1 minus a minus x is the sum from n equals 0 to infinity of minus x to the n on this open interval. So what this tells us is that -2 over x squared minus 1, which is 1 over 1 minus x plus 1 over 1 plus x, should just be equal to this sum plus this sum, which is equal to this sum right here. And this is the power series for this function on the interval from -1 to 1. All right. Now I'm going to let it be your turn. Using those same kind of properties, I want you to find the power series of x over x squared minus 1 on the interval from -1 to 1. And my hint is to use partial fractions. So for this one, the first thing you're going to do is to express this as a sum of a over x plus 1 and a sum of b over x minus 1, and figure out what the power series are of these expressions, and then you'll know how to combine them to get the power series of the term on the left. All right, let me know if you have any questions. I'm happy to help you with this one. Have a good day.